And today we're going to hear about his latest work on patterns of sunlight on exoplanets. So please join me in welcoming Tony.
Hi there. Okay. Well, thanks for that introduction. And actually, I'm talking about a whole series of 3 papers I did, and why I did those I should share with you. And that's because I got tired of reading the same conventional wisdom all the time, and that's given here. Okay. It's often said exoplanets, their stars, are unsuitable for life because they always keep the same side towards their suns. So their water and other volatiles freeze out on the dark sides. Well, this is driven by an analogy with the Earth's moon that always keeps the same face towards us, of course. But in the case of extrasolar planets, it's misleading. And we have a nice counterexample in our own solar system. Mercury, which is the planet closest to our sun, is in what we call a 3-to-2 spin orbit resonance, which means, like it says here, it rotates 3 times during every 2 orbits. This situation is depicted here in a nice figure from a paper by Dermot. You see the reference? If you look at it in an inertial frame, like you're just watching from some distant point in space, Mercury is this 2-toned football-shaped object. At periapsis, when it's closest to the sun, its long axis points towards the sun. Okay, but then it's rotating 1.5 times as fast as its orbital rate. So that means that by the time it's gone halfway around the sun, okay, it's rotated 3/4 of the way around, and now its short axis is pointing towards the sun. And as it comes back around to perihelion again, it's rotated 1.5 times, so now the opposite hemisphere is facing the sun from last time. And it goes around again, and then the original hemisphere comes back and faces the sun. So if you look at this as if you were riding on the surface of Mercury, you would see the sun going around the planet in this complicated double loop, where it tends to hang around the long axis of Mercury close to the planet, and then it goes around this long arc over the far from the short axis, and then it comes back around the other end of the long axis and repeats this situation. Now it's going in the opposite direction to the orbital motion. Okay, that keeps happening. Okay, so why do we care about this? Well, as you can imagine, this kind of a motion leads to very complicated temporal cycles of insolation. By insolation, I mean the heating from the sun and illumination as well. And this has significant implications, not least for the detection of infrared emissions from extrasolar planets that might be doing something similar, and also the interpretation of their emissions. And of course, this kind of pattern of insolation has profound effects on a planet's climate and naturally its habitability as well. Okay, so now this kind of thing can happen if a planet is in an eccentric orbit, as Mercury is, for example. So we have to take a little closer look at eccentricity. So as we know from Kepler's first law, planets go around their stars in ellipses with the sun or a star at one focus, as depicted here. Here's the star at the focus, and the eccentricity is a measure of how far the focus is from the center of the orbit, and it's measured in units of the semi-major axis, which is just half the longest diameter of the orbit. And there are other parameters like the semi-minor axis, the periapsis distance, which is the closest approach to the star. And there's another thing which is called the semilatus rectum, or sometimes just the parameter p, and it's defined that way. Not to be confused with big P, the orbital period. Now, it's interesting to notice, as you probably know, the orbital period is a function only of the planet's semi-major axis, and also it's the mass of the star times the gravitational constant. Similarly, the energy of the orbit depends only on that semi-major axis. But there's the angular momentum per unit mass, which I'm calling little h down here, which depends both on the semi-major axis and the eccentricity of the orbit. This is going to be interesting later, but notice for now that this angular momentum is proportional to the square root of this semilattice rectum. Okay. So let's just look at the actual eccentricities of some extrasolar planets. Here I've plotted the 627 extrasolar planets now known with known semi-major axes and detectable eccentricities. There are more that are nominally have zero eccentricity, but those are generally not well determined. As you can see, these eccentricities range very widely from practically zero down here all the way up to nearly unity, which would be the limit for a bound orbit. While the semi-major axis is going down from less than 1/100th of an AU up to more than 100 AU, where, of course, the 1 AU is the distance from the Earth to the Sun. But notice also that the eccentricity is correlated with the semi-major axis. There's this, let's go back here. I've gotten ahead of myself. Okay, there's a roll-off where the orbital eccentricity, come back, is lower for the smaller semi-major axes. Okay, and that's universally attributed to, let's go back, come on. This keeps advancing. Can we stop that somehow? Keep clicking? Okay. Yeah, all right. So this roll-off is attributed to dissipation in the planet of tides raised by the star. So the star raises tides in the planet, and the energy is dissipated by tidal friction. Now, that, as we know, since the orbital energy is dependent on the semi-major axis, that causes the semi-major axis to decay. It also causes the eccentricity to decay because although the orbital energy is decreasing, tides do not change the angular momentum of the planet. So as A is decreasing, 1 minus E squared has to increase to compensate, so E itself has to decrease. That's why both E and A decay together. But also notice that since the angular momentum doesn't change, the semilattice rectum doesn't change either. So if we go back and we change this plot, now watch the points up near the top, from E versus A to eccentricity versus semilattice rectum, these points shift over to the left. And now, whereas formerly planets under the influence of tidal dissipation would travel down this plot kind of diagonally, on this kind of a plot, they move straight down because the semilattice rectum is conserved. Okay, so when I originally did this back in 2007, I had only 1/3 as many planets, but the pattern was the same. It hasn't changed. Okay, so well, in addition to decreasing E and A, tides in the planet also tend to reduce its rotation rate and its obliquity. What do I mean by obliquity? Here I'm defining it as the angle between a planet's spin and orbital angular momenta, as defined by the right-hand rule. There's a nice little figure for you. Sometimes it's defined as the angle between a planet's equator plane and the orbital plane, but this is more convenient because it helps to define a retrograde rotation that's more than 97 degrees, which is not all that uncommon. Okay, so tides decay a planet's rotation rate as well as its obliquity, but not necessarily all down to synchronous rotation or down to zero obliquity. There are many ways in which it can hang up, especially if a planet's orbit is eccentric. And the details of that process depend on the model you use for tidal dissipation. Here are a couple of models. There are two main ones. The less common I've plotted here as a solid line. It's called a constant Q model because except for a sign change when it crosses to 0, the drag on the planet, the rate at which the rotation rate decreases, is pretty much independent of the frequency of the tides, which is related to the rotation rate. It's the speed at which the bulge due to tides moves across the planet. This is appropriate for solid body friction. An analog would be if you were pushing a book across a desk, the resistance tends to be independent of the speed at which you're pushing it. Now, on the contrary, the more common model is called the viscous model, or the laminar viscous model. I've drawn it here as this kind of diagonal dashed line. And this is appropriate more for like a lubricated kind of friction. You could also imagine, what's nice about this model is that it's analytically convenient. For example, for most tidal models, you have to Fourier analyze all the different components and frequencies that occur in the problem. And for the viscous model, you don't. It's analytically much simpler. But that doesn't mean that it's realistic. In fact, you could imagine a turbulent analog where the drag force is proportional to the square of the frequency, as happens, for example, with eddy viscosity in a fluid. But a more realistic model may be this dot. Hello. There we go. This dot dash curve, which is a Maxwell or viscoelastic model. This applies to a substance like a tar or silly putty or a lot of other things. For short time periods, they behave elastically, but over a long time scale, they flow like a liquid. Well, which of these is actually right? Well, there's recent work that shows that geologic materials tend to behave like something in between the solid and the dot dash curves. Their tidal response is pretty flat as a function of frequency. It doesn't matter a great deal which tidal model you use, except that the constant Q and other models that are close to it and fairly realistic tend to lead to enhanced probabilities of winding up in a spin orbit resonance. Okay, like the synchronous resonance, for example, is one of them. But there are other resonances that occur for when the orbit is eccentric. Let's look at the case where the eccentricity is 0. Here's a planet which is not in any kind of a resonance. So it's just spinning independently of its orbital motion. And it's also got 0 eccentricity or obliquity. So I've drawn this kind of map of the insolation across the planet as a, where we go, as a function of latitude and longitude. Okay, and I've shown the maximum insolation across the surface and its mean over time. Okay, the maximum insolation peaks at the equator, as you can see here, and its peak value is just what I call the extrasolar constant, analogous to the solar constant on Earth. It's the star's luminosity divided by 4 pi times the square of its semi-major axis. Okay, and you can define that in any kind of wavelength regime you're interested in. But okay, so I've drawn, in addition to these contours that are plotted down at the bottom, I've drawn a contour at 99.99% of the maximum, so that you can see it's along the equator. There is where the peak insolation occurs, and then it drops off as the cosine of the latitude to 0 at the poles. And the mean insolation behaves similarly, except you divide the maximum insolation by pi to get the mean. Okay, that's if the planet is not resonant. But now let's look at the synchronous resonance for comparison. Now here I've plotted the same kind of thing, except the maximum insolation and the mean insolation and the minimum insolation are all the same because it never changes. Here's a planet that's always facing onto its sun, and the sun is hovering right over the subsolar point there, never moving, and this entire hemisphere is illuminated, and the illumination drops off as the cosine of the latitude, the distance from the subsolar point, until you get to the terminator, and then the whole far side of the planet is dark, and that's what the blue contours are for. There's no insolation there at all. Now, okay. Again, that's a synchronous resonance, but if you look at the 3:2 resonance as Mercury is in, okay, let's see how that behaves as a function of eccentricity. Okay, now this is from Brown et al., and they used to plot it up, a slightly different color scheme than I did, but there are color bars here to help you figure it out. Okay, now for a zero eccentricity, the insolation pattern, and this is the mean insolation, is pretty much the same as if the planet were not in resonance at all. But for an eccentricity of 20%, 0.20, like up here, as Mercury has, you can see that there are two hot spots on the equator where the planet's long axis is, and it's cooler in between with a short axis, and it falls down to 0 at the poles. As you raise the eccentricity of the orbit, that pattern pretty much persists until you get up to a regime change here at about an eccentricity of 70%, where it starts to look again like the non-resonant case. But when you go past that to an 80% eccentricity, the insolation flips around so that now the short axes are hot and the long axes are cooler. But still, the insolation vanishes at the poles. Okay, well, again, this is as a function of eccentricity, but there's still no obliquity in the problem. So let's consider what is the effect of a planet's obliquity. Okay. Again, here's to remind you about what the obliquity is. And the obliquity in the solar system varies a lot among the different planets. For extrasolar planets, it's essentially unknown. So it could be practically anything as far as we know. So, but the effect of obliquity on the insolation can be very significant. For example, here's again a non-resonant planet. It's on a circular orbit. This plot is again from somebody else, Linsenmeyer et al., and they have a different color scheme. But this shows the situation. For a zero obliquity, the insolation as a function of latitude, come back, peaks at the equator and drops off to 0 at the poles. Now, as you increase the obliquity, the situation becomes less extreme. The poles get a little more sunlight until when you reach a point around 50 degrees obliquity, the insolation, the mean insolation, is almost independent of latitude. As you go on farther to high obliquities around 80 or 90 degrees, the poles actually get more sunshine than the equator does, and so they become presumably warmer, and the equator becomes cooler. Okay, now that's a non-resonant planet. Something similar happens if you have a planet in one of these spin-orbit resonances. For example, if you're in the synchronous resonance, the sun moves up and down across the equator, but it stays on the same side of the planet. This shows that situation for a case of a 45-degree obliquity, but this is a synchronously rotating planet, no eccentricity. And so the sun tracks this kind of a loop, figure 8. It looks like the analemma that you find on many terrestrial globes. This figure is actually the same as the intersection of the surface of the planet's treated as a sphere with a right circular cylinder that's tangent from the inside. And so we're going to see this subsolar track again in in a moment. Okay, so how does this motion of the subsolar point affect the insolation over the surface of the planet? Well, here's a case for a synchronously rotating planet. Again, there's no eccentricity, but I've given this an eccentricity, an obliquity of 30 degrees. So if you look at the maximum insolation up in the top panel here, you can see that 99.99% insolation contour is making a figure-8 loop that's just tracking that analemma, the subsolar ground track. There's also, and you can see that the insolation is very high on one side of the planet, but it vanishes on the far side. The same goes pretty much for the mean insolation. But if you look at the minimum insolation down here in the bottom panel, you see that it vanishes in all that blue over most of the planet, except that there's a region near the mean subsolar point, the front of the planet, which is in permanent daylight. Okay, and the same applies if we change the obliquity. If we go to 60 degrees, that region of permanent daylight shrinks, and likewise the regions of permanent nighttime shrink as this figure-8 track of the subsolar point broadens in latitude and longitude too. Okay. Now if we push on to an obliquity of 90 degrees, okay, what's going to happen is, first of all, the minimum insolation vanishes, so I don't even plot it. It would be all blue. The maximum insolation is shown by this top panel, and you can see that the track of the subsolar point now goes right over the pole, making this sort of X contour here of 99.99% solar constant insolation. And now there is no point on this planet where the insolation vanishes entirely. There are some areas that have pretty low insolation, but it never goes to zero. And so that means that the climate is going to be a lot milder than in the previous case. Also notice that the mean insolation here at the near the subsolar point has now split into 2 peaks instead of 1. Pressing on to 115 degrees, if we go retrograde now, just to see what happens. Now the subsolar ground track wraps around the planet, and the peak of the mean insolation has now split into 3 parts, 3 peaks at the center here. And keeping this up, if we go to 140 degrees, that peak insolation in the mean has reunited into a single peak, but notice that the minimum has now split into 6 minima across the planet. Okay, if we kept going to 180 degrees, it would look like it wasn't resonant at all. Okay. All right, so far that is what happens if you have an eccentricity only or an obliquity only. Because notice these have 0 eccentricity. But what happens if you have both eccentricity and obliquity at the same time, which is presumably the general case? Well, it gets a little more complicated, as you might imagine. And so we're going to need to define a new angle. Actually, I'll define a few here. This situation is best visualized instead of as the planet going around the star, have the star go around the planet. Imagine you're riding on the planet, and this is the celestial sphere as seen from the planet, centered on the planet, but it's not rotating. Okay, the planet is rotating around in this system, but this sphere is centered on the planet, and so this horizontal oval here represents the equator plane of the planet. The tilted oval represents, in this frame, the orbit of the sun going around the planet. Okay, and okay, so the sun is going to be at some location given by some latitude and longitude, which I've drawn here, and so the sun is going to be here at any moment, and its location is defined by a couple of angles. The true anomaly, which is how far it is past its perihelion, periapsis, and this angle alpha, which is going to be significant. It's the, in this view, it's the sun's longitude of periapsis. But if we went back to the solar-centered view, it would be the planet's longitude of vernal equinox. That's the thing that precesses with the precession of equinox. I'm going to define just a couple more quantities here. Little omega is the planet's rotation rate, and n is its orbital mean motion. That's just 2 pi over the orbital period. Okay, so we're going to need these to understand spin-orbit resonances. It's convenient to divide them into 2 classes. And the first is the integer spin-orbit resonances. And by that I mean that this ratio of the planet's rotation rate to its mean motion is a whole number, like 0, plus or minus 1, 2, 3, etc. Now, the 0 and the negative resonances are not very important, so I'm going to concentrate on the positive ones here. And so all these resonances have certain characteristics which we're not going to bother to go into in detail. It's better just to look at some more maps. So doing that, first let's look at the synchronous state where you have both eccentricity and obliquity happening at the same time. Now from here on in, because I have to vary alpha, and 3 parameters is too many, I'm going to stick with an eccentricity of 0.2 and an obliquity of 60 degrees. Okay. So here now that precession angle, alpha, is set to 0. And you can see that now these looping curves are, again, the track of the subsolar point. And the contours are as before. The colorful contours show the insolation. You can see that now this analemma type figure 8 is tilted, and so are all the other features of the insolation. This region of permanent daytime and the region of permanent nighttime, etc. But the insolation, both the maximum and the mean, both peak near the center of this illuminated face. As we change the parameter, the angle alpha, as it's going to precess, here we get, as is the case for 45 degrees, you notice that the configuration has changed, the shape of that subsolar ground track has changed, and the contours have changed too. If we push on to a 90-degree alpha, we have yet a different figure.
Pardon me, can you remind me what alpha is?
Alpha is probably best regarded as the longitude of periapsis of the sun. Okay, we'll take another look at that. It's how far perihelion. It's pretty much how far the perihelion is from the equator. Okay.
Along its orbit track.
That's right. That's right. Not its latitude, but its distance along the track from where the node is, where it crosses. Yeah, the longitude of vernal equinox is another way to look at it. Okay, but the important thing is that it varies. It circulates through 360 degrees over a moderate time scale. Okay. All right. Now, so I've gone from 0 to 90 degrees. If I were to go past 90 degrees, another 45 degrees to 135, the figure that I would get would just be like the mirror image of that one. If I went to 180, it would be the mirror image of this one for 0, and so on. So basically, these couple of figures cover the whole range of the space, pretty much with various reflection symmetries and so on. Okay, that's the synchronously rotating case. By the way, I want to point out that these extra colors that you're seeing in the top panel, the purples and the greens and so on, are because of the planet's eccentricity causes the insolation to exceed the solar constant, or the extrasolar constant at those locations. So I needed some extra colors for that. Okay, now here is the situation where we're in a 2-to-1 resonance now. The planet is rotating twice as fast as its orbital mean motion. And again, that means that the entire planet gets illuminated from time to time, so there's the minimum insolation everywhere is 0. Every place experiences day and night. So I haven't bothered to plot that, just the maximum and the minimum and the mean insolation. Now here's the track of the subsolar point. As you can see, it's traversing the entire planet from east to west, as a matter of fact, and the contours of illumination follow along accordingly. As we step through the precessional angle, you can see how that subsolar track and the corresponding contours evolve through 90 degrees, etc. So there are these really fairly interesting peculiar patterns you get. The contours are pretty angular and not at all rounded and smooth as you might expect. Okay, now the same thing goes for the 3-to-1 resonance. We're still on the integer type resonances. Now the subsolar ground track wraps around the planet twice per insolation cycle, and that changes with alpha as well. And just one more here. If we go up to a 4-to-1 resonance, now the ground track is wrapping around 3 times, and the insolation is changing accordingly. But as we go to higher and higher resonances, the contrast in these plots is decreasing. As we went to very high order resonances, numbers of, say, omega over n is 10, 20, or higher, these plots look almost as if the planet were not resonant at all. They become independent of longitude and depend only on latitude. Okay, so that's the general behavior of these integer resonances. But there's another class which are called the half-odd integer spin resonances. That's a mouthful, but the reason is that now this ratio of rotation rate to orbital motion is half of an odd integer. So it's plus or minus a half, 3 halves, 5 halves, etc. And this has its own characteristics, but the important one for our purposes here is that now the subsolar ground track and the insolation pattern that goes with it repeat twice around the planet. I'll show you what I mean. Here's a case for the 1/2 resonance. So the planet is actually rotating slower than synchronous in this case, but it's a valid resonance. Now the subsolar ground track is going from west to east, but it's still bobbing up and down over the equator. Notice now, though, that everything is happening twice. So if you will, the eastern and western hemispheres of the planet look alike. Okay, and as we evolve through the precessional angle alpha, that remains the case, etc. All right, now let's go back to the resonance that we know well, the 3 halves resonance, like Mercury is in. Of course, Mercury has practically no obliquity. This is a case where what it would be like if it had a 60-degree obliquity. Now the ground track is going around from east to west again, and the pattern of insolation is repeating twice, just like the ground track. And we'll step through this one. 45 degrees. Now the loops are changing, and you're getting some cusps down in the southern hemisphere, etc. And you get these really, I think, kind of bizarre patterns. If we go up to a higher resonance still, this is the 5 halves resonance. Now the subsolar track is going around. It's still east to west, but now it goes around 3 times, wrapping around the planet. And again, the peak insolation is repeating twice around, so is the mean insolation. And you can see how that evolves with alpha as I step through this. Okay, so this goes to show that you can get some interesting patterns of insolation varying across the planet. But there's one more surprise in this, and that's the following. If you notice this plot down here, the mean insolation looks to be symmetrical across the equator. The northern hemisphere is like the mirror image of the southern hemisphere. And if we go back, okay, let's stay here. Notice that is not the case. That is not the case for the maximum insolation, and it certainly isn't the case for the subsolar ground track. If we go back and check, it's still true as we change alpha, it's still true for this 3/2 resonance. The northern and southern hemispheres look the same for the mean insolation, and so forth. In fact, this remains true for every half-odd integer resonance that I've looked at. Well, okay, how about those integer resonances? Well, we'll just run back through them very quickly. Well, no, it's not happening here. Notice that the northern and southern hemispheres are different in all these plots. As we go through, it remains true. In fact, for all of the integer resonances, it's not true. So we have this interesting phenomenon that for the half-odd integer resonances, the mean insolation is symmetrical between the northern and southern hemispheres. Okay, well, why is that? Well, I have a convincing explanation for it, but it's kind of unsatisfactory because, again, it involves a lot of Fourier analysis, and I'm hoping that I or maybe somebody in this audience can do better than that and come up with a nice, simple, clear explanation for why that's happening. Meanwhile, we can draw some lessons from all this. Okay, so we know that extrasolar planets could be in a wide variety of spin states. Okay, we don't know, but the dynamics indicate that there are a lot of possibilities. Also, I've shown you that these unconventional rotations cause pretty complicated patterns of insolation across the surface of a planet. As a general rule, these unusual insolation patterns produce a milder climate because the insolation is more broadly distributed, and you might expect that to improve a planet's habitability as well. And last, but I guess not least, the unusual insolation patterns affect the detectability of exoplanets in the infrared and the interpretation of such observations as well. Okay, so I'm going to leave it at that, and I'd be happy to take any questions at this point.
Tony, I was wondering if from your patterns of insolation here, whether it's possible to infer the spin states of the exoplanets that we might see in the future. What sort of possibilities?
Oh yeah, that speaks to this interpretation issue, because if a planet is detected, for example, by its infrared light curve, okay, or let's say that a planet may be known, but its light curve is measured, the pattern of variation may not be what you expected, but it may indicate that the planet is not in some simple synchronous rotation, but in one of these more unusual spin states.
On a billion-year time scale, you would expect the orbital eccentricity to damp out to zero, especially in the case of planets orbiting close to a red star. Why do we see so much eccentricity in the data that's been collected so far? And why do you think Mercury still has non-zero eccentricity?
Okay, well, we do see evidence, as I showed you near the start, that a lot of planets have lost eccentricity. But the fact is that because there's so much more angular momentum in a planet's orbit than in its spin and its rotation, that the rotation state of a planet changes tidally much faster than its orbital eccentricity decays. So a planet can maintain orbital eccentricity for tens of billions of years in some cases, while its spin state has changed drastically.
Can your analysis help understand the Gregorian calendar and why we have 4 years of 365 days, and then we have to add a day? Is this something that would fit into your analysis?
I'm afraid I'd have to say not really, because the Earth's rotation rate, which defines the length of a day, is pretty independent of the length of the year. And it's just coincidence that it happens to wind up at 365 and almost a quarter, but not quite.
So it's a coincidence. It's not.
That's right.
Very complicated resonance.
Yeah. Now, if we were on Mercury, we'd have a very interesting calendar, I'm sure. But that's not the case here.
Yeah, a couple of simple ones. I'm a little puzzled as to what it means to be in resonance if the obliquity is 180 degrees. What does a one-to-one resonance mean?
Okay.
And is that something that could actually, you could get tidal evolution into a state like that?
Okay. You can formally examine what would happen to a planet whose rotation rate is equal to its orbital rate. You know, if the periods are the same for any obliquity, but there is no dynamical benefit for a planet to be in a synchronous rotation rate or any there's no benefit for a planet to be synchronous with a 180-degree obliquity. I take that back. Actually, there is a mild interaction, but it's very weak compared to the usual synchronous resonance. So it's kind of let's put it this way: it's an unlikely event to find a planet with a really high obliquity, like 170, 180 degrees, that's also resonant.
And what obliquity does this getting captured in the resonance begin to become very unlikely?
I'm afraid I have to confess that that is unknown.
Is it known which evolves more quickly, the obliquity or the spin rate?
They evolve on comparable timescales.
Okay.
The obliquity maybe half as fast as the rotation rate.
So I'll continue about dynamics. So something like Earth or super Earth would probably have its shape dictated by rotation rate, unlike Mercury, which preserves some kind of solid shape. And also, you know, the obliquity will be determined by the spin state through Cassini state and all that. So have you looked into the dynamical part of it beyond geometry, of what is more likely than other states?
Yes, I have.
Okay, if that's the entire answer. My question is, your last lesson there, insolation pattern affects exoplanet detectability by infrared. I'm sure it does. How does it? Does it make it easier? Does it make it more difficult? Does it make it easier in some circumstances?
The latter, yes, it depends. Because sometimes,
Give some examples.
I don't have an example for you right now, but there are sometimes where the admission is not where you would expect it, but it's someplace else. And so it depends on where and when you're looking. Okay.
Hi. On the third point about improved habitability, so if you had a planet that was in a habitable zone that was, say, almost entirely water covered, would a complex pattern of insolation distribute the heat more efficiently so that the ocean maintained a more uniform temperature than, say, Earth?
Yes, that's my conclusion.
My question was also about lesson number 3. Is there any program to actually produce global climate models for such weird insolation patterns?
There was a first attempt, actually, that just came out. Let me just see whether I can flip to it. Because, let's see here. Yes, this came from a preprint where these individuals attempted to study the potential ecological niches on a planet in the 3-2 spin orbit resonance. Okay, I think there was another question or two.
Yeah, I have another one. I assume if the planet had a moon, that would make things even more complex, as I believe it does with the Earth.
Okay.
Any more questions?
Okay, thanks a lot.
Okay, Tony, I have a, I get to, no, stop clapping. I get to say when the clapping starts. Not, sorry, Tony. Here we have a special SETI black mug for you to cogitate over with some black material in there as well, and while you're thinking about patterns of sunshine on exoplanets in the future. Please join me in thanking Tony for his great talk.
Okay, thanks a lot.
Feel free to come up and ask questions of him